Let's explore the fascinating phenomenon of negative capillary resistance, where less pressure can produce more flow. Imagine a thin glass capillary touching soapy water on a warm plate. When you reduce the pushing pressure, the meniscus actually moves faster into the tube. This counterintuitive behavior arises from surface tension gradients. Let's understand what negative capillary resistance means and why it matters. In typical microfluidics, we expect that more pressure produces more flow. This is the standard behavior. But with Marangoni effects from surface tension gradients, the device can behave like a tunnel diode, where less pressure actually produces more flow. Here's a flow versus pressure curve showing negative differential resistance. In the middle region, increasing pressure actually decreases flow velocity. This enables passive pumps, oscillators, and diode-like flow control without any moving parts, making microfluidic devices simpler and more reliable. Let's calculate whether Marangoni forces are strong enough to matter. The Marangoni shear stress is approximately the surface tension temperature derivative times the temperature gradient. For water, the surface tension temperature coefficient is about 1.6 times 10 to the minus 4 newtons per meter per Kelvin. Consider a modest temperature gradient of 1 Kelvin across 10 micrometers. This gives a gradient of 10 to the 5th Kelvin per meter. The resulting Marangoni stress is about 16 pascals, which is comparable to pressure drops in millimeter-scale microchannels. This diagram shows how Marangoni forces of 16 pascals pull along the interface, strong enough to drive significant flow in microchannels. Now let's understand the counterintuitive mechanism behind negative resistance. When you push hard, you wash out the surface tension gradients. The flow is too fast for gradients to build up. With gentle pushing, surface tension gradients can build up and stabilize, creating stronger pulling forces along the interface. This comparison shows how high pressure washes out gradients and produces slower flow, while low pressure allows strong gradients to build, producing faster flow. We can model the pressure balance as delta P equals a U minus C of U, where a U is viscous loss and C of U is Marangoni assist. The viscous coefficient A equals 8 mu L over R squared from Poisson flow. For a radius of 50 micrometers, length 5 millimeters, and viscosity 0.001 Pascal seconds, we get A equals approximately 1.6 times 10 to the 4th Pascal seconds per meter. If the Marangoni assist slope exceeds the viscous slope, we get negative differential resistance. The total slope d delta P over du equals A minus the assist derivative. When this is negative, we have backbending. Let's see how Marangoni forces modify standard capillary filling dynamics. The baseline Lucas-Washburn law says position squared is proportional to time, so velocity decreases as inverse square root of time. The velocity u equals x dot and is proportional to t to the minus 1/2. A Marangoni boost acts like extra driving pressure and can counter this slowdown, especially at late times. The augmented equation is x dot times x equals the capillary term plus r over 2 mu times delta gamma for the Marangoni contribution. For radius 25 micrometers, surface tension 0.07 newtons per meter and contact angle 0. The capillary coefficient C is about 0.44 square meters per second. A small surface tension difference of 1 millinewton per meter adds 0.0125 square meters per second, a few percent boost that matters when filling has slowed. This graph compares Lucas-Washburn filling alone versus with Marangoni boost. The boost keeps the meniscus moving at late times when pure capillary filling would have slowed significantly. Temperature gradients create Marangoni flows from hot to cold regions. Surface tension decreases with temperature, so the hot side has lower gamma and the cold side has higher gamma. This gradient creates a net pull from the hot region toward the cold region along the interface. This diagram shows how a droplet on a hot-cold stripe experiences Marangoni forces pulling it toward the cold side. The Marangoni number quantifies the ratio of Marangoni forces to viscous diffusion. For water with length scale 1 millimeter and temperature difference 5 Kelvin, we get Marangoni number around 5,700, much greater than 1, meaning thermal Marangoni strongly dominates viscous diffusion. This makes thermal Marangoni a strong candidate for creating negative resistance regimes in microfluidic devices. Let's summarize the key insights about negative capillary resistance. Surface tension gradients from temperature or concentration create Marangoni forces on the order of tens of pascals. Strong applied pressure washes out these gradients, while gentle pressure allows them to build and dominate. The result is that flow velocity can actually increase as you decrease the applied pressure in certain regimes. This phenomenon enables passive microfluidic pumps, oscillators, and flow control without any moving parts. Thermal Marangoni effects with Marangoni numbers exceeding 1000 provide ideal conditions for these behaviors.